The final way that I can determine whether I have a relative maxima or relative minima is called the second derivative test. It's a little bit harder to understand. It's not quite as obvious as the first derivative test was, but when using it to justify why things are the way they are, second derivative test can oftentimes be a little bit faster. There's less to say to make it true. I don't need to do this hand waving about derivatives to the left of a value and derivatives to the right of the value. I can just talk about the second derivative. And the test goes as this. So if I am given a function f of x such that f prime of x naught equals 0, okay? This automatically tells me that f is continuous at x naught. What this means is one of two things. So given that, if f double prime, the second derivative of x naught, is less than 0, meaning that if we are concave down, then let's just say x naught f of x naught is a relative max. And I'll come back and explain this after I show the other piece to it. If f double prime of x naught is greater than 0, meaning concave up, then x naught f of x naught is a relative minimum. Okay, so why is this the case? Well, what we have here right now is the following. I have f prime of x naught is 0. That means at x naught, I have some horizontal tangent. Okay? But in this first case, if f double prime, the second derivative, is less than 0, that means it has to be curving downwards, concave down. And so if it's curving downward and hits a horizontal tangent up there, we can see that we must have this relative maximum value here. Or it's also clear that I must go from increasing slope to decreasing slope. So I could sort of support the second derivative test using the first derivative test. So, but it's worth thinking it through. Concave down means that I get a maximum value. The other way now, same idea. If f prime of x naught is 0, I have this horizontal tangent right here. It's going directly left and right. But if f double prime is greater than 0, that means it's concave up. It's curving upwards. So, like this. And we can see now if it's curving upwards, it must have a relative minimum there. And so a little bit faster to justify whether it is a maximum or a minimum using second derivative. But also, it doesn't always work. You have to have the derivative exist. So if I had a corner, I could not possibly use second derivative test. I could still use first derivative test to show things. And for all of these tests, except for graphical, really, I'm just looking at relative maxima and relative minima. I can't make the argument with these tests alone about what's the absolute maximum or absolute minimum.